Thank you for this new event that we started to run, which is called Neural 2020 Neural Emergent Property of the Connected Brain. This is a workshop where we will teach you a little bit of the theories that is behind all the tools that we developed over the past 15 years with the following people, like so myself, Stéphanie Fockel, Flavio Delacroix, Ahmad Bey, Hervé Lemaitre, Chris Foulon, Anna Matsulevitz, Valentina Pacella, and Marcela Ovando-Teles, who has a paper in under review at the moment, but she will present it next opus of this workshop when the paper will be hopefully accepted. So here's a program. So yesterday, for some of you, we made the informal meet and greet at the Connemara pub. That's why some of us have bigger bags than others. We've been discussing intensively yesterday. Today, we'll work mostly on diffusion-weighted imaging. So we have the chance to have Flavio Delacroix, who's been, who's in the back right here, who's been my reference for about 20 years now. When it comes to do tractography, he's really good. He developed the spherical deconvolution algorithm. He'll teach us like the latest development, why we should use it, how to use it. And he has his own software that is in the list of software we sent to you. We will show you the advanced tractography, and then this afternoon, Ahmad, who's not here because he's in the States and due to the political situation, doesn't want to get out because he's not really sure he can get back in. We'll do via Zoom some explanation how to do the data pre-processing, and then Steph will show you how to dissect the language system. Tomorrow, Steph will start with the concept of emerging properties applied to language and the function ectome, and then you have some practical explanation from Hervé Lemaitre, who's a very awesome guy that we have right behind with a beard. That will show you how to do fMRI analysis, and then I'll give you some examples of how to use the function ectome, which is just a little plug that you had to your fMRI analysis. So there's no specific new way of changing your procedure or processing fMRI, you just transform your data. And then all afternoon we'll play around how to process fMRI, so we finish the week or at least the day with a good glimpse on how to process fMRI dataset. The day after that, we'll speak about brain lesions and brain disconnection. I'll show you the basics with Valentina Pacella will show you the basics and the advanced way of looking at brain disconnections and linking it to behavior or outcome in patients. And then in the afternoon, Anna Matsulevitz will show you how to use artificial intelligence to speed up the production of disconnection maps and potentially for you to plug it into future foundation model, whatever you want to do with it. And I'll show you toward the end a little bit of the disconnectome symptom discoverer, which is a platform that we created to predict symptoms 1 year after the lesion. In the evening of Wednesday, we have this social dinner. We booked a fantastic restaurant. We're going to have a lot of wine and good food, but we still at 9:30 having a presentation that is of great interest, which is called Navigating Emerging Property in Neuroscience, that I attributed to myself because I always take the next day hangover of first presentation. That's a classic. I always had this one. Then Valentina will talk to us about tripartite disconnection, which are advanced way of looking at how different disconnection relate to outcome in patients. Then Chris Foulon will show you his software that is still in development. Chris Foulon was right here, Valentina Pacella next to him. Which is Emergence, which is a software that allow you to capture emerging properties. And it's not only for neuroimaging, it's also for any kind of data, whether you use an Excel spreadsheet, neuroimaging, images, sound, it will allow you to do analysis in it. And Then we'll speak a little bit of hands-on on preparing data sets in the afternoon of the day, so that like the next day on Friday, we can full work on your own data set and try to debug any kind of struggle you can have with your data and try to give you some guideline how to process it and to extract values or do your analysis. So you finish the week with, at least on your laptop, some things that function and a strategy to move on for your research. This is a new recipe of how we organize the workshop. So we used to do tractography workshop in the past, and then we moved to do brain hacks that are more like really interactive way of all working together and doing research. And this is a mix and match of the two, with lecture at the beginning around the new concepts, these emerging properties, with the opportunity to also have interaction in the afternoon. But your feedback would be always very welcome, because as it is a new recipe, we'd like to know how to adjust to make it the most effective possible in the future. You will see that you have also some material. So we sponsored by the new Vascular Brain Health Institute, which is dedicated to the study of vascular disorder and preventing vascular disorder, which started last year. We hope you'll hear a lot about this in the future. So they gently offered us like this little booklet that we can write on if you want. You have the program inside as well. So if you lost at any point, because I'm not going to keep that slide all day, you can always come back here, know exactly where we're at. And you also have the special issue of Science, where we designed the cover with Stephanie Fockel, where you have the latest update on tractography and also as a depiction of our paper on the theory of emerging properties and how actually a connected brain could be a good model of systems that work as with emerging properties. All right, so without further ado, I'll try to bring you into like the concept now. Okay, so we're all here because we like to do science. There is only really one way to do science, is to rely on observation, to elaborate theories and models of the nature and behavior of natural things. I didn't invent that. The person who invented the scientific method is Bacon, and did it in 1620. That was a long time ago. And since then, we didn't change our approach, because this is the best way to actually demonstrate what is true about life and the environment around us. But it works on a tripartite interaction between theory, methods, and observation. Sometimes people start with a theory and make some observations, but we need to use a method to sharpen our eyes. You use a microscope, for example, to see things that are not visible with your naked eye, or a telescope to see in space things that are not visible with our naked eye. But as we're using those methods that sharpen our vision, we also bias our observation, which is already a bit biased with our eye. And so what I'm trying to explain to you is that through the change of method, you can change the observation and change the theory, how you interpret the functioning of the disorders of the brain. Another important thing is some people also rely a lot on theory. We work a lot in the brain on the neuronal theory. You might think that it is something that is sure and acquired today, but there are like many other different cells in the brain that we fully study and understand their role into cognition or functioning of disease of the brain. We'll touch a little bit of that on Thursday. What we're going to try to teach you today and the other day is a little bit of the theory of emerging properties and a little bit of the method that allow you to study it. Okay. Mostly, bases we're working on are onto localization of function in the brain. And why is that? It's because we observed patients that had very specific injury in the brain that are related to a very clear outcome. You have the case of that guy. Do you know who it is? Yeah, exactly. What happened to him? Yeah.
It's a train track, right? Or...
Yeah. It was a construction worker building a track. I've been telling that story for 10 years. So it was a construction worker head of a little team building the path through the rock for a railway to go from east to west of the United States. It was during the exploration and motivating like Americans to go live inside in the west of the USA, and transportation was the best economical way to, best strategic way to do that. But unfortunately, due to a terrible accident, when he was like tamping some powder inside a rock, like the powder, explosive powder like exploded and pushed the metal rod that he's holding in his hands through his skull. So he entered under his cheekbone, popped out his eye, and came out at the top of his brain. So you have here a reconstruction of the brain with his skull. The brain is coming from an average brain because he's been exhumed and there was no brain anymore. So we just have the skull. And the bar, you can see, really damage the frontal lobe. And because his personality changed so much after the accident, he became very aggressive and behaved in a way that was not his habit before. People interpreted that as the orbitofrontal cortex. You can see damage here by the entrance of the bar was really the main site for the control of behavior and personality in the brain. And so that's very important because at the 19th century, where people think that personality belongs to the soul and it's all related to religion, and we have this case that for the first time is saying, well, actually it's ascribed to matter and you can destroy it. And it's very changing the way people look at things. But at first sight, do you think like a damage like this is a good example of damage of the orbitofrontal cortex and is linked with behavior? What's wrong with that? Nothing's wrong about that?
It's not only orbitofrontal cortex.
Yeah.
Damaged.
Right, that bust had to come out some way on the top, and it could very much be the SMA and pre-SMA that was responsible for the symptoms. But people really bias their eyes and want to see what they want to see, and they describe what they want to see, really. There's this other case. Unfortunately, we don't have the picture of the patient, but does that ring a bell? It's actually two different cases on that slide. Do you know who it is? That's right, and name is written. It's not Paul Broca at all.
Patient done.
Yes, it's 10 on the left and in the middle. It's actually written on the bottom. It's Lelong at the second patient. So both patients were studied by Broca, same thing, toward the end of the 19th century. And so at that time, there was no imaging. You found those interesting patients that couldn't speak, and then you had to wait for them to die to get their brain out and hope you'll find a lesion somewhere, which was fortunate enough for Broca that he managed to have those patients dying during his lifetime, because cannot happen the next day unless you're a very bad surgeon, which we won't go to right now. And so both patients couldn't speak and had this lesion in the posterior part of the inferior frontal gyrus, an area that Broca decided to call the Broca area because he's very humble. That was related to the production of language. And here you have Nina Dwongers, who was the first in 2007 to scan the brain of Le Borgne, sorry, on the left, and shows that actually behind the surface there was a lesion that extended deeply inside the white matter. That's an interesting example because you see how observation can be biased if you just look at the surface of thing, and when you start looking at it, just for example, slicing it, you will see other things that will change your observation and interpretation just because you change your methods. It's just a simple example, but maybe that could have been the Broca track or fasciculi instead of the Broca area. All right, let's move on to this case. Ring any pound. So exactly, that's HM. So HM was a patient with intractable epilepsy, and he had at the age of 27 a surgery from a very zealous neurosurgeon that decided to remove on both sides the medial part of the temporal lobe. That was how it was happening. You were using like this little tube and like sucking out part of the brain in the patient. And the patient came out just fine after the surgery. He was able to walk, he was able to count, he was able to speak. A real success according to neurosurgeons, but unfortunately, he was not able to build any new episodic memory, as well as lost like about 10 years of memory before his surgery. So the interesting part here is that for some reason, when you think about HM, everybody think about hippocampus and memory. But the entire medial temporal lobe was removed. The hippocampus, only the entire part of the hippocampus was removed. And the amygdala was removed in both sides of this patient. So when you do clinical neuroanatomical correlation using that case, don't think about just the hippocampus. There was like other areas that were damaged. But those three pillars of like the way we explore the functioning of the brain and its relationship to brain lesion are the reason why we had this representation of the brain as being built as several tiles that are functionally specific. Okay, so you have the tile for the production of language, the tile for the episodic memories, and you have all the organization of the motor cortex and all these visual modules, and everything is divided in the brain. And that's been sort of supported by looking very close at the organization of the neurons in the cortex that you can see here in those very nice depiction from Golgi and Carl, who push very much toward the neuronal theory by just defining that there is only two kinds of cells in the brain, neurons and non-neurons, which is a dominant, sorry for Spanish people in the room, it's a dominant way of thinking that is inaccurate because there are like many different other cells that should have their own category that are not only non-neuronal cell in the brain. But if you look at the organization of neurons, you can see that the brain can be parcellated in different regions according to the profile of the different 6 layers of the cortex, sometimes 3 layers or no layer at all for very old cortex. And so you can see that they have different profile, and people have been dividing the brain accordingly into regions, thinking that the structure, the spatial organization of those neurons is a sign of a functional specialization. Okay. So there are some of the most advanced relationships that have been done in the old time by the Vogt and Vogt couples, where they started like labeling onto the brain the function that will be associated with those different parcels. And the latest neuroimaging division of the different region, cytoarchitectural region of the brain based on several brain. So that's a very big, the original one was based on single brain that was sliced. This one is neuroimaging group based. And so you can find that the work of Katrina Muncis is a life achievement. She must have spent like 30 years on this, and the map are available online. And that's a little bit the context in which I was born as a scientist. And to try to explain to you how we get to the emerging property, I thought I'll give it to you as a perspective of my PhD, where I was supposed to try to understand what is visual neglect and how does it happen in the brain. And somehow starting with this kind of vision of the potential site that I linked with visual neglect, which is classical neurological impairment that you can find after a lesion in the right hemisphere, where people do not pay attention or are not aware of anything that happened on the left side. They shave only half of their face. They will only eat half of their plate. They will neglect half of the world as if it never existed. And then somehow many studies that were looking at lesion or brain stimulation in surgery were reporting that it could be either in the frontal lobe or in the parietal lobe or in the temporal lobe. I think some people mentioned the occipital lobe at one point. So pretty much like anywhere in the brain can lead to this syndrome. Doesn't really fit the idea that you can have this one tile that will be visuospatial neglect in the brain. And it was very disturbing at that time because it was the dominant model. We tried to look at this closer in neurosurgery. Sorry, it's still morning. If you're low skimmish and you don't like blood, close your eyes. Where I designed this experiment where you do line bisection, so you have to put the center inside a long line and try to see whether the patient is deviating or not deviating. Was a neurosurgeon on the awake patient is using an electrode for small electrical stimulation of the brain regions. And when we were stimulating the cortex, we surely had some small deviation towards the right of the true center. They were significant where we're stimulating the posterior part of the superior temporal gyrus or the supramarginal gyrus, which was very much fitting with the mess that I showed to you just before. But then in another patient, when we start like digging deep inside the subcortical structure, which is a white matter, and start like putting the electrodes onto the wires, we starting having those very, very strong deviation to the right of the true center. That led us to think that there is no tile really for this function. This function is working through the interaction between brain areas. And that was the beginning of wait. So white matter is just not a cable linking brain areas. It is maybe linked to true function. Yes.
You try simultaneously stimulating multiple regions to see if you
All right.
the effect
Yeah.
you get with the...
It's a very good question. Some people do that. Those are living human people. So there's a limit to what we can do and how much stimulation we can do in principle. But some people have been doing that. They also did stimulation and recording at the same time. But the objective is really, you always have to explain that the objective is to prevent symptoms. And then stimulating at two sides at the same time is maybe harder to justify, but I don't know, maybe it's...
When you do this kind of surgery, you don't stimulate in multiple places in the same time because the goal is to reach the functional boundary.
Yeah, okay.
But you can stimulate in multiple places when you use SEEG, for instance, and record in the same time.
And so we were very interested to see how much white matter seems to be more related to function than actually simple cortical sites. And then later on with Flavio, when I was doing my postdoc, we looked at the same connection that we stimulated, but like with the advanced method that Flavio made available for us to have full reconstruction in healthy controls. And we found that the lateralization of those connections were extremely correlated to the behavioral outcome in healthy controls. And that's why we were like, there is really something going on, not in the way the neurons are organized in your cortex, but maybe mainly how they are speaking to each other between brain regions. That seems to be extremely related to function in itself. And there must be a mechanism, a reason, a functioning of the brain that we're missing through this kind of local investigation that we classically do with MRI. So that brought like a lot of interest and advance into the study of brain connections, as you can see here. If you look at the PubMed number of papers that came out looking at brain connections, it's been exploding over the past decade. and we had the chance with Steph to be invited like 2 or 3 years ago to write this review about the current state of connectivity study, and that's why we brought forward the idea that actually studying connectivity is not just studying the wire, is studying a different way of functioning of the brain that some people thought about before, which I'm going to come to, which is looking at interaction, synergy between brain regions, integration, or emergent properties, which are like 3 different ways of looking at this mechanism, but that's the same idea behind it. So you're not clear about emerging properties. This comes from the Gestalt theory that come directly in opposition with the reductionist theory in philosophy and psychology. So the reductionist theory, you know it very well. It's like if you have a problem, you can split it into pieces and study those pieces separately to try to find the solution to your problem. The Gestalt theory is like the whole is more than the sum of the part, so you cannot dissociate part of your problem in order to find your solution. You have to look at as a whole. There is no right or wrong in those approaches. The emerging property and Gestalt theory is harder to do because interaction can be infinite, and the reductionist approach is way too simple to really resolve the brain. And we're trying to find our way a little bit in the middle between this. I usually use that example to explain to people what emerging properties are. So let's imagine aliens abduct you and put you into the spaceship. You can find yourself in there. And the ultimate goal is to try to understand, because alien scientists found this object on the planet, which is called a book. And the ultimate goal is to try to understand how it works. Why is it so important, and why do people pay so much attention to books? Probably move to phone now, like the new generation don't read books, but you get the example. And they put their best reductionist scientists onto the problem that took those books and shredded into pieces and then started to look at it with a microscope, every single pieces. And then they took every pieces and they put it back together at the atomic level. And then use that into the spaceship is like, take these fake books that I've been creating and tell us how it works. And so you take the thing, but because they put it together at the atomic level, but did not capture the interaction between the different part of the book, the different pigments inside the book are not forming letters anymore. They're not forming words, paragraph, and story. And that book is nonsense, and they completely failed to capture the essential thing, which is the story of the book, which is the emerging property of the interaction between the different parts of the books. Okay, same thing for neurons. I like science fiction. I took this example recently I saw in this cheap movie called 10%. Listen to that.
1 is their unit of measure, but it's not. All social systems we put into place are a mere sketch. 1 + 1 = 2. That's all we've learned. But 1 + 1 is never equal to.
That seemed cheap, but it's pretty deep if you think about it. Because take those books, what is life? How chemistry become biology? Life is the emerging property of the interaction between chemical elements that we still do not explain very well. In the Song of the Cell, Guy spent his entire life studying cells. It's like, we still don't know why the cells of your body are staying together to work together to make you a being, while they don't just like go rogue and do whatever they want to do. And so the idea is like, if that's the case for life, if that's the case for the cells, brain is made of cells, that could very much be also the case for the brain and for the way it's functioning. It's only working through those interactions. Bring it down to very, very close. If you look at those 2 neurons in the Petri dish, they're exactly the same. They will put all their efforts all the energy into one single goal, which is connecting together, maybe in a creepy way, but that's what they want to do. And then you will see that despite not being different at all from one another, through this connection, they are becoming different in the way they connected to other neurons. And that's what makes a specialization. If that's what makes a specialization, that's what makes the other function as well. Okay? So, yeah, we were not the first to think about this, and a lot of this has been forgotten. I like Marinette. He's the one who described for the first time the different category of fibers, and we'll speak about this a little bit later with a functionectome, where he divided the organization of the brain into projection fibers, that are fibers that are in the center of the brain, all the spinal cord that project onto the surface of the brain. In sum, if you want to simplify, it's pretty much an interaction between the external environment and to your brain, but that's not all, okay? You have the commercial fibers, that are those fibers that connect the left and the right hemisphere. You might think, yeah, why not? That could be useful. Some of us heard about split brains. But that's also what allows you to have a panoramic vision in front of you. Otherwise, you'll have something split, you know? That's and it's pretty smooth. I don't see any limit between the two. It's on my nose, but yeah, it's pretty good. And then you have those association fibers that are pretty fascinating because they're fast track between two regions in the brain in the same hemisphere. Why is that? So costly in terms of evolution, so fragile, like 10 centimeters, very thin cable. Of course, it's going to break when you have a stroke. And of course, it's going to be terrible for the functioning of the brain. But maybe this is critical and essential to its functioning. That's why it's there. Usually use this example of a baby trying to reach out a candle, a flame. If you know babies, they're really attracted to shiny stuff, but they will do that mistake only once. So you see how the flame with the eye is going to go through the chiasma and then the thalamus to the optical center and then project into the rest of the brain. That's how you are like, oh, wow, it's shiny. I want to touch it. Then you program the reaching of the flame with your motor cortex, and then you're going to reach the flame. But unfortunately, you'll burn your hand. And then you have sensory ascendant fibers that will bring you to the thalamus and the sensory cortex. This pain of burning that takes a long time because those fibers are poorly myelinated. This is what happened phenomenologically, but then you don't touch the flame again. Why? No. Yes, you learn through the association between what you saw, what you did, and what you felt. How do you make an association between all these centers? Association fibers. That's why it's called association fibers. Skip like 200 years, and then this is what we thought about with Steph, is like technically the function is not in area X, Y, or Z. The function is through the integration of the effort of those brain areas, at least function as we know it. Because the granularity of how we study function in the brain is quite poor. We build it and we also, that also later, mostly on observing patients that had problems and being like, what can this problem be? And that's how we define a new function. Oh, it doesn't speak. Maybe a function is speech, or it doesn't remember. Maybe a new episode, because the rest he can remember. Yeah, that's an episode. Well, we're gonna call it episodic memory. That's how it is. But also, if you think the brain as a machine and the different configuration that it can take to model experience or memory, if you were to take a localizationist approach for 3 given brain areas, X, Y, and Z, you can only have 3 different states that are possible of activation or no activation. So your system will do 3 states, and you can remember 3 simple things, or you can do 3 actions, and that's it. If you take like another model, which will be the classical associationist model, is this hierarchical organization. A speak to B, speak to C, and then you move your arm. Then it's even poorer with like 3 regions. You only have 2 configurations at all. You activate the circuit or you don't activate it. If you speak about emerging property, which would be a pattern that can change, then possibilities are almost infinite. I mean, like not in the case of 3 regions, but you can see how you exponentially can increase the number of configuration. That's model here between the modular. That's why I'm talking about tile and specialization. As a hierarchical organization, the integrative, you can see as you increase the number of regions, you increase the number of possibility of states that your system can take. And this is not innocent, because when you open your laptop every day and you want to do an analysis of the brain or imaging, whether you use a method or another method, what you're going to see and the theories that you work on belong to a complete different school. So if you open your laptop and you do some voxel lesion symptom mapping for voxel-based morphometry, some cortical thickness analysis, or task-related fMRI PET-EEG or MEG, when you compare one location with another, well, you belong to the school of Paul Broca and his Broca area, and himself belonged to the school of Joseph Franz Gall, who was the guy behind the phrenology that said if you use an area very much, it'll be bigger and will deform the skull and you have a bump. Those are your people. And if you use a different software, like if you do some tractography, trigrass analysis, functional connectivity, effective connectivity, anatomical connectivity, function ectome, whatever you want, then your people are Theodore Minard with his baby trying to touch a flame. Carl Wernicke, who was the first to say a lesion will impact a network, and created this large network of language area interacting together with different kind of flavor of disorder you can have according to the disconnection you have. In the model of the left, the brain is organized as a group of tiles that are independent from each other, and the damage that you can have to your behavior or cognition is only related to the area that has been impaired. In the model on the right, the brain is made of interconnected network, and the flavor of the damage that you can have will be related not only to the area that is damaged, but the network of areas that have been impacted, either through inhibition, because it's not excited anymore by this area, or disinhibition, because it used to be inhibited by this area. Complete different theory of the brain, different methods, different observations, different model of how that works and how that can dysfunction. But then, if you move on to our 3 guys, and then you don't look at the location of the lesion, but you look at the pattern of lesions they can have, then you could have a complete different interpretation. And the disorder in the behavior of Phineas gauge is not coming from a lesion of the orbitofrontal cortex. It comes from a disconnection of many tracks in the frontal lobe, including this frontal track that allow to maintain and plan your day. And that's why in the depiction of his recovery, he went out in the middle of the winter in Vermont. It's really cold. In pyjama pants and sim boot, and almost died from the cold after almost dying from a bar going through his skull. That would be a shame. As well as the disconnection of the uncinate fasciculus, which I do not recommend doing this at home. If you cut the uncinate fasciculus of your cat, it will become a very bad cat, very aggressive, not the cat you used to know. In the case of Le Bon, it was not only a lesion of the Broca area, and as Nina Drongas have been showing, it extended largely into the white matter, disconnecting many of the track of the perisylvian, including the arcuate fasciculus that we know is critical for language. And finally, Henri Mollesen had a bilateral lesion of the medial temporal lobe. So not only damaged the hippocampus, as we said, and the medial temporal lobe and the amygdala, but disconnected the entire limbic system bilaterally, where you had a disconnection of the fornix, disconnection of the cingulum, and a disconnection of the uncinate fasciculus. So the disconnection of the fornix is interesting because sometimes patients have a cyst right in the front of the fornix. A neurosurgeon, for practical reasons or lack of skills, transect the fornix and the patient comes out. I'm done, this is my last slide. Transect the fornix and then the patient come out with episodic memory impairment, cannot create this new memory of episodes. Or when you look at Alzheimer's disease, those different spots here, like you have the hippocampus, here you have the retrosplenial cortex, here you have the anterior cingulate. Those spots are where you have most of the amyloid, most of the reduction of the cortical thickness, most of the hypometabolism in Alzheimer's disease. And Alzheimer's disease is characterized as a main sign as a loss of episodic memories. And the uncinate fasciculus in monkeys also, when it is disconnected, is associated with a lack of possibility to create memories associated with emotions. And that might seem far, but don't you remember more things that are related to an emotion than things that were pretty dull? Be honest. That's actually a strategy to remember better something. And with this, I'll leave you with Flavio Delacroix. We will take the rest of the morning to speak about diffusion weighted imaging and advanced tractography. Thank you very much.